and hit the start button, and then you're live.
The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to Preventing Operational Failure webinar series. I'm Lou Hoffus, Predictive Maintenance Analyst for Troy Industrial Solutions. I really appreciate everybody who's participating today, and let's take a look at our agenda. Today, in the world of reliability, we're going to look at corporate trends. We know the pains, the challenges you face. We're going to discuss the true cost of downtime, the challenges you're up against, the cost it hits into your pocketbook. We're going to look at the evolution of maintenance. We're going to look back as far as the 50s, see where we're at, where we're going, and where we want to be. We're going to place a particular emphasis on the proactive precision strategy, and we'll discuss that at length. We're going to look at our toolbox, the supplies necessary to keep on hand. We'll look at case study of a company that realized the benefits of the proactive strategy and realized really a great bottom line, and we're going to share that with you. We're going to give you a call to action. Where do we go from here? What resources can we send you away with? Can we give you some takeaways? What's the next step? All right, without further ado, let's go right on to the next step, and that's going to be looking at corporate trends. Today, we are all faced, we hear it all the time, companies are downsizing. We're trying to automate to do more with less. We're taking machines and we're replacing humans. We're working with smaller maintenance staffs and crews. We've forced ourselves into like a firefighting mentality, where you might have an employee who's putting out a fire on a particular machine, trying to fix it, and another call comes into the maintenance office, and it's a higher priority, and he's pulled from there and goes to the higher priority. It's just a constant battle where your smaller crews are firefighting. We're placing an emphasis on reducing costly spares kept on hand. To reduce the bottom line, spares sitting on the shelf are becoming worn before they're put into use. It's costing us a lot of money, and that's just another challenge that we're faced with out there. The production-oriented run philosophy, we're called to be competitive. We need to continually run to maintain inventories. The production people don't want to give us enough time to work on our machines. And along with that, we're being forced to take machines that were designed years ago and to run slower machines beyond the design specifications. And this faces yet another challenge to our maintenance crews. The emphasis to improve the bottom line is time after time we hear that we need to cut costs. We need to figure out ways where we can cut spending and improve our bottom line. And just everywhere I go, they want to eliminate unplanned downtime because it's just one of your greatest costs. It's the number one concern where the money's going today. So, what is the true cost of downtime? Well, if you look at a contrast of unplanned versus planned repairs, you can relate well. If you have a surprise in the middle of the day and you're already working with a low-man crew and you've got to call folks in, you've got to find the parts, you're going to have an extended down period, and that just turns into cost after cost. Secondary damage, I want to stop here for a second and explain what I mean by the secondary damage principle. What we're looking at is, I can give you an example. We have a fan that's in imbalance. The machine is moving pretty severely. It's been like that for quite a while, and then it fails catastrophically because we didn't repair the imbalance problem. The bearings failed. In the case of a motor, there was too much pressure on the motor bearings, and now we ended up replacing the rotor and the stator or even the whole motor. So an inexpensive balance job just turned into a replacement of a complete piece of equipment. Now, safety issues, there's always a potential for somebody to get hurt when motors are worn or bearings are failing, equipment is not running in its tip-top condition. We have a potential for injury, and that's something we're always trying to eliminate in the workplace. Quality issues. If we have worn or displaced parts, you might have printability issues, you might have formation issues on a paper machine. There's all sorts of quality issues that can go hand in hand with not maintaining equipment correctly. This MRO inventories, this is the expensive spares, once again, that are kept on hand. Now let's look at the overtime costs. If we have a piece of equipment that's down and we have to have people stay, the challenge, first of all, is to get people to stay past 4 o'clock a lot of times. And then even getting folks to come in, it's extremely costly. Now we're extending into contractor costs. Once again, it's just a time factor. Getting them on site, doing the safety training. All these are delays, and it's downtime. No production is occurring. And this can even work into environmental issues. If a machine is not working correctly and levels aren't maintained correctly, we could have spills, reportable incidents, and that leads to a potential for fines. In the power industry, if you can't turn your generators on when they're called for, or they go down when they're not planned to, there is fines that are possibly issued. So let's take a look at where are you at now. And when we look at this, we want to look at how we evolved throughout the years. The first one we see here is run to failure. In the 50s, this was very popular. It's breakdown. It's also known as reactionary or hysterical. There are some benefits to that, and there's some drawbacks. We have preventative maintenance, which was calendar, planned, or historical. Predictive maintenance, which was condition-based. And now the philosophy is getting more towards the proactive, precision-based reliability, or proactive. So with all of these, they have their advantages and disadvantages. With breakdown maintenance, the advantages, there was no cost that would be related to the condition monitoring and preventative maintenance. Machines are not over-maintained. The disadvantages, unanticipated downtime. There's potential for secondary damage and even catastrophic failure. There's a loss of production, high repair costs, and the worst, a lack of control. Now when we go to our preventive maintenance, we really thought we were ahead of the game. We were replacing equipment on a calendar or a planned fashion before it failed. Maintenance, one of the advantages was that maintenance is performed at a convenient time and in a controlled manner. Unexpected machinery failures should be reduced. Therefore, there's fewer catastrophic failures and less interruption to production. There is greater control over the parts stored and cost. The disadvantages, machines were frequently repaired when there was no problem. Repair actions often caused more harm than good. And there's still unscheduled breakdowns. Now, this brings into a case where we replace a piece of equipment, and the term infant mortality has surfaced during this time, because we would replace a motor that was running perfectly fine and put a new motor in its place, and we went to start up, and for some reason it died on startup, and that was called infant mortality. Now, with the age of instrumentation and going to predictive maintenance or condition-based, we had the advantages of unexpected downtime is reduced. The parts were only ordered when we needed them. We were using these instruments to give us an indication of when we had a problem. We were only working on the equipment that had an issue. The disadvantages, these instruments cost a lot of money. The system, the services, and the personnel, there's a tremendous lead time of getting somebody up to snuff and operating a vibration analyzer or a thermal imager or a motor testing device. You don't just get these pieces of equipment out of the box, and they don't just come up and say exactly what's wrong. You have to interpret the data. And finally, it does not ensure that the machine life is extended as a disadvantage for predictive maintenance. So finally, we're at the proactive or the precision-based, which is using a combination of what we learned in predictive maintenance, but it brings into account other pieces of equipment. And it also adds some advantages such as equipment life is extended, the equipment reliability is improved, there's fewer failures and thus less secondary damage. There's reduced downtime, and we reduce overall maintenance cost. Remember, we were using the same instruments that we were utilizing in predictive maintenance, so we have the same disadvantages: the cost of the instruments, the systems, the services, the personnel, the additional skills required, and additional invested up front is huge. This might be where you look at your outsource decision. This requires a complete change in philosophy on the part of management and on down. So, placing our emphasis on the precision proactive strategy, we want to help you to define some of the action steps that are utilized in this and the objectives. With precision proactive strategy, we marry predictive with the precision, like I told you before. We're going to identify critical equipment. This is the equipment flow. This is the particular pieces of apparatus in your facility that will affect the whole plant. Some equipment, like we said, it's still cost effective to run to failure. In some cases, people still blend preventative maintenance, but we're finding that the precision proactive strategy, and I'll give you a case study later, that it's really starting to pay off for folks. They're using the third entry here is the development of trend data. If you can imagine, we're reading vibration analysis figures or current figures on a motor, and we are seeing the same readings time after time. And later on in the year, in the fall, all of a sudden we see large increases, and the trending data goes up. It's going to give us the ability to recognize early warning signs. Sounds, the way we go out and we do rounds, we look at things. Some companies are using ultrasound listening devices. They're placing their hands on the equipment and helping to recognize early warning signs. But we want to really stress that we need to start looking at using advanced instrumentation techniques to get early warning. Now, how about identifying the potential of failures or hazardous conditions? We'll know this ahead of time if we get current increases, or we're reading vibration data or thermal imaging data or ultrasonic data that tells us that something's changed. And one of the most important elements of the precision proactive strategy is we're not going to just replace a piece of equipment and allow it to fail again in the same manner. We're going to look at other methods of testing to eliminate repeat problems. And we're going to finish up with an engineered solution. Great example, we had a company had an extremely weak base under a motor in a feed water section. Come to find out that plant was built over a swamp, and the resonant frequency of the floor and the way that everything was designed was extremely high movement. Every time we put a motor in, it would go right to high movement with certain pipe conditions, and the solution was to completely remove the base and form it with the appropriate mass. So the precision proactive activities. What are the methods that we use to get to where we want to be? We spoke earlier of trend analysis. All of these instrumentation devices that we utilize have the ability to take data and measure the current situation under certain load conditions, and it records it. If we log all this data and record it over time, and we make a particular note in this trend data, will take all of this time data over time and create lines and graphs. We can look at root cause and failure analysis, and we can take all this information together and arrive at conclusions that either it's in good shape or it's in bad. Now, when we do have something fail, the root cause and failure analysis, which is we're going to disassemble, we're going to tear apart our equipment, and we're going to look at how each particular piece of equipment failed. For instance, we have a bearing that failed. It was tested under vibration analysis conditions, and we found a sharp upward trend with impacting. We'll disassemble the bearing, we'll cut it apart, we'll look at it under a microscope. We might even utilize oil analysis and other forms of root cause to figure out what was a leading indicator for this to fail. It could be corrosion, it could be overloading, a cocked bearing, but we're going to investigate it, and as I said previously, we're going to engineer the problem away. So, other tools, moving on to vibration analysis, which can measure machines oscillating about a reference. There's 3 types of vibration out there that we're concerned with, that we measure. We're looking at free body vibration. We're looking at meshing and passing, which would be like gear meshes of gears on a paper machine, or a blade pass of a fan, or the blade passing of a pump. And a large part of our vibration analysis looks at frictional vibration. The information that vibration analysis can give you is going to be multifold. We can see what the information is known as forcing functions. And the forcing functions could be a fan that's in imbalance. Remember that the definition of vibration, vibration is simply the oscillation about a reference point. A shaft vibrates relative to its casing of a piece of machinery. A bearing vibrates relative to its bearing housing. Vibration exists when a system responds to some internal or external forcing, excitation, or some type of function. When it breaks down, those 3 previously mentioned forcing functions will cause abnormal vibrations, and we can measure changes in amplitude. We can look at vibration over time, the acceleration, and all sorts of different types of vibration characteristics. Some of the functions might be imbalance, misalignment between 2 given shafts. We can see looseness. We can see gear mesh. There'll be the blade pass, like I mentioned earlier. Soft foot, whereas if you can imagine a bolt on one of the feet that holds a motor down and comes out, and all of the shims are missing, and you can see that foot freely moving. That's an exaggerated form of soft foot. Other functions, bearing impacting. If you have a fault, say you're doing a down day on a paper machine and they squirt a lot of water all over this machine to clean it, and for some reason some of the chemicals in the water got in the bearing and it caused some corrosion on the inside, and eventually as the bearing elements pass over that corrosion, it will cause the surfaces to gall, and eventually you'll see an impacting when we take our vibration readings. Other things happen. Machines move. It never fails a shaft to move, and it will cause a rubbing. We can see this. We can even see lubrication issues with vibration analysis, and we can detect, and it will give a leading indicator if we have, in fact, an electrical problem with our vibration analysis. Thermal imaging is an instrument which will take readings that can only be seen with the thermal imaging camera. It's the light waves that an eye cannot see. All bodies of any type of equipment above absolute zero emits infrared energy. Infrared energy is captured by a thermal imaging device, and it puts it into a visible image. Many of the thermal imagers today can capture a thermal image. They can also capture a digital image, and then we can put a voice print on it. That makes it very valuable information because we know where we took the image, we know where we were because of the voice annotation put on it, and then it can be rapidly put into a report format. The thermal imaging may give us signs of a rub or friction. You can look at 2 driven bearings. One, it'll show a differential between the 2. The suspect bearing could possibly be overheating. Alignment problems can be seen with thermal imaging, but it's really very helpful with electrical anomalies such as a looseness or an overloaded lug, corrosion in connectors. They'll show up very well with thermal imaging. Laser alignment and balancing supports our precision maintenance philosophy. Vibration analysis will find a misalignment, and vibration analysis will find balancing problems, but our advanced tools, the laser alignment tool and the balancing tool, will help those problems go away so we don't have a repeat offender. Ultrasonic testing utilizes the ability of the science for an instrument to hear sound waves that are beyond the human ear. And a great example, any type of released like steam, air, water in a body rushing past an orifice, they give off ultrasonic sound waves. With the corona of arcing conditions inside switchgear, there's all sorts of elements that we can use to hear beyond the range of the human ear. The EPA published findings that ultrasonics can save you thousands of dollars by finding lost air. I'm going to give you an example in the EPA published report. A 3/8 inch leak in a year will cost you approximately $3,000 in energy cost by trying to create that type of energy to just basically losing it. All right, so motor analysis is one of our new activities. It's also known as PDMA testing. Motor analysis utilizes software and hardware to look at 6 fault zones in and around a motor's electrical circuit. The instrument can be applied to the output of a drive or a switch system going to a motor, and it can test everything, the entire electrical path. It can look at the fault zone of the air gap. The air gap fault zone describes the measurable distance between the rotor and the stator within the motor. If this distance isn't equal throughout the entire circumference, the air gap eccentricity occurs. That varying magnetic flux is measurable, and the analyzer will see it. The software package will flag it and record it and give you an alarm. And this condition can cause harm, and it can actually cause a dangerous condition within a motor. The fault zone of insulation. The insulation fault zone refers to the condition of the insulation between the windings and the ground. Electrical equipment operates properly and safely, but it's important to know that the flow of electricity takes place along well-defined paths and circuits, and that it shouldn't be leaking from one path to another. The deterioration of this insulation within these motors can result in really unsafe conditions. You don't want personnel to be exposed to that type of leakage of current. Once again, this instrument would detect that. The fault zone of the power circuit. The power circuit refers to all of the equipment or conductors and connections that exist from the point at which the testing starts through the connectors of the motor. So like I said, you can go all the way back into the motor control room. This instrument can be connected live while it's running. Of course, you have to take into account your arc flash hazards and your NFPA 70E, all of the prescribed hazards. And there's even special connectors for doing medium voltage that can be applied ahead of time. It can include the circuit breakers, the fuses, the contactors, the overloads, the disconnects, and the lug connectors. Research on industrial power distribution systems have shown that the connectors and conductors are a source of approximately 46% of all faults, reducing motor efficiency. The power quality fault zone from the motor analysis PDMA device focuses on the condition of the voltage and the current in the motor's branch circuit. Poor quality can greatly affect the operation and health of the electric motor. It puts a lot of stress on the motor. Like I said earlier, vibration analysis would see these faults. It would see that there's an electric issue, but the motor analysis PDA instrument would narrow it down to where the problem is. The other fault zone, two remaining fault zones are the rotor and the stator, and this software actually goes out and checks the rotor and the stator for the proper integrity of the rotor bars, the rotor laminations, the end rings, the squirrel cage, and so on. And in the stator, the fault zone, it causes early detection and prevention of the motor failure surrounding the stator windings. Stator windings are the heart of the motor, producing the rotating magnetic field, the induction current, and the torque to turn the motor and the rotor shaft. So that's our tools of the trade, the tools in our toolbox for the activities. Let's take a look at the advantages that one particular company found by utilizing predictive maintenance services, utilizing the precision proactive strategy. In this particular case study, occurred in 2013. It was a paper machine felt guide roll. There was 8 hours of downtime that would have been, let me back up a little bit. What this is representing is the cost savings that were avoided as a result of catching this problem with vibration analysis and other forms of predictive maintenance services. They predicted, the company that had this particular felt roll predicted that if it had failed, if we didn't detect it on a down day, or this was detected while the equipment was running. If we didn't detect it, it would have cost 8 hours of downtime, approximately $1,900 per hour of production loss, 32 hours labor times $52 per hour loaded, $1,500 in a general repair, which that would be the representative of secondary damage. The total cost avoided was $18,364. Now, this company uses an outsource predictive maintenance services, and the cost of the services for that day were paid for around well over 10 times. Now, let's move on to further study. This company looked at their benefits of the precision proactive strategy over an entire year. Now, they stated that a paper mill bottom line improvement to be world class at 2.5%, and they looked at their unscheduled annual downtime. They had a target for 2012, and the target was 2.8%. When they looked at the results of all the graphs and all the readings of their downtime for the year, they came out to 1.4%. They were available 7,200 hours, 7,200. The production cost is approximately $2,000 per hour. So we took the target and minus the results and went times the number of available hours times 2,000, and they realized $200,000 of operational savings net in the bottom line. It looks like your maintenance department is making money for the company here. So that's an actual case study of a working mill utilizing the precision proactive strategy. So, where are you? Now, here we are at the bottom line, the takeaways. What are you going to do? Are you going to do nothing? Are you going to hide your head in the sand? And maybe you need to do more research. Maybe you're, at the end, I'll put my my email address on there. Maybe you want to have me come in and help you do a self-evaluation. Maybe you want more research. Don't put it off, because you might think you can afford this, but you can't afford not to. You do yourself a cost analysis, and the small price of performing the precision proactive strategy is going to pay off in the long run. And you ask, do you need help? And if you do, I want you to feel free to contact me. I'd love to discuss it. If you want this precision proactive strategy lesson, or you want to look at preventing operational failure, or you want to look at vibration analysis, thermal imaging, we can discuss that. We can pull everybody into one of your training rooms and talk about that. Get a hold of your territory manager is another method. I want to leave you with some resources that I utilized for this presentation and that we use at Troy Industrial Solutions. We prescribe to some of the newsletters that come out. You've got reliableplant.com, plantservices.com. Mobius.com is where we get our level 2 vibration analysis certifications. We frequently utilize PDMA.com. There's a wealth of information that would help you to look at the fault zones, more information about PDMA, testing and motor reliability. A reliability web has just tons of information about everything I talked to. It's the buzz out there, what we're talking about here. And then, of course, feel free to visit our webpage, TroyIndustrialSolutions.com. And you'll notice that we have a 1-800 number on there. If you feel free to contact us anytime. Let me go to the last page here. You can see my email address, lhoffis@troyindustrial.com. I want to thank you for attending, and I want to reemphasize, if you want some mentoring, you need some help, you don't know how to go about the next step, we'll help you at any level that you want us. If you want some additional services or where to look for the instrumentation, we'll give you a hand. I really appreciate the opportunity talking with you today. Thank you for attending. Be sure to stay up to date at troyindustrial.com for future events. We will be giving some more of these webinars, and we'll record this one here today. We'll put it up on the website, and we'll make it available so that you can utilize it at your facility. Thank you very much, and have a good day.